Probably the most important application of the sampling theorem is to process continuous time signals in discrete time and then interpolating them back to continuous time outputs. This allows, for example, to implement continuous time filtering using a digital computer by sampling, applying a discrete time filter on the computer, and then interpolating back the result into a continuous time output. This is, for example, what's happening right now as I speak into this microphone, into this camera. It's exactly the process, because at the other end you have a continuous time output again. We are also going to look at the dual case when we start with a sequence, we interpolate to go to continuous time domain, we do continuous time domain processing, and at the end we sample to get back an output sequence.
Module 6.6 Discrete Time Processing and Continuous Time Signals. The overview is that we're going to look at the impulse invariance between a continuous time system and a discrete time system. This is extremely important because it allows to compute a continuous time convolution, for example, using a discrete time convolution. This is a very common application of discrete time signal processing. We'll show the duality when we can compute a discrete time convolution in continuous time and discuss a few examples. The basic setup is the following. We have a continuous time signal xc of t sampled with a sampling interval ts. Then we have a discrete time filter h of z. Then we do interpolation again with ts as a sampling interval to get an output yc. So the question is, this red box, what is the equivalent continuous time filter capital H c of j omega? Assume xt is omega n band limited. Then we know that the sampled version has a discrete time Fourier transform x e to the j omega given by this formula. It's a rescaled version of xc. Then the output of the digital filter y e to the j omega is simply given by the convolution theorem. It's a product of the two DTFTs. And the output is going to be a scaled version in frequency of the spectrum of y. To be precise, the frequency omega is multiplied by Ts, and there is a scale factor of Ts also in front. In sum, Yc is equal to the product of Xc times the discrete time Fourier transform of H, the sequence of the discrete time filter, rescaled, and we point this out, Hc of j omega is equal to H of e to the j pi omega over omega n. This means h of e to the j omega is 2 pi periodic, so this function is 2 omega n periodic. This is what we call the impulse invariance between the discrete time filter and the continuous time filter. Let's assume that the discrete time filter is a half-band low-pass filter, so it has perfect passband from 1 to pi over 2 and perfectly zero outside of this band. What will happen as we implement this filter in the system we have seen before is that everything gets rescaled to fit within the band minus omega n and omega n, so this half-band filter remains a half-band filter, but now with respect to the half sampling frequency or the Nyquist frequency omega n. Let us do an example of a half-band filter implemented in discrete time but that processes a continuous time signal. So we start with a spectrum between minus omega n and omega n. We map it into a discrete time spectrum between minus pi and pi by sampling at twice omega n. We apply the discrete time half-band filter between minus pi over 2 and pi over 2. And then we get the blue spectrum. We reinterpolate and we get the red spectrum, which is now a half-band version between minus omega n over 2 and omega n over 2. That example should be very explicit here on how this works on processing continuous time signal using discrete time filtering. Let us compute an example in detail. So the goal is to design a discrete time filter to isolate a band of frequencies between 4000 and 5000 Hz in a signal that is band limited to 7 kHz. 7 kHz band limit, it means we need a sampling frequency at least twice that much, so 14 kHz or higher. For simplicity, let's pick the sampling frequency of 16 kHz, or omega n is 2 pi times 8000 radians per second. We need a bandpass of 1000 Hz bandwidth. And to do this, we're going to start with a low pass of cutoff 500 Hz, so it will live between minus 500 and plus 500. Then we'll modulate it to 4,500 Hz, and it will have a bandwidth of 1000 Hz centered at 4,500. So here is the desired low-pass filter in continuous time. So it has a 1000 Hz bandwidth. It will be modulated to be centered at 4,500 Hz. And in discrete time, because of impulse invariance, we will have an omega naught, which will correspond to 4,500 kHz, and a bandwidth of 1000. And we need to calculate these numbers to design the discrete time filter. So the cutoff of the low-pass filter is simply capital omega C divided by capital omega n multiplied by pi, and that's equal to 0.0625 pi. So modulation frequency is simply pi times 4,500 divided by 8,000, that's 0.5625 pi. Then we design an FIR low pass with cutoff omega C using some method that you can choose. Finally, we multiply the impulse response by 2 times cosine omega naught n. This will modulate this low-pass filter to the proper location, which through impulse invariance will be 4,500 Hz. We just saw how to compute a continuous time operation in discrete time. How about the dual situation? So take a sequence xn, interpolate a continuous time signal, apply a continuous time filter Hc, sample, and get an output sequence yn. The duality of impulse invariance that we saw before allows to understand discrete time operators in continuous time, and sometimes this is very intuitive. For example, we'll see differentiation, which is very simple to do in continuous time, but actually difficult in discrete time. So the question is, what is the equivalent discrete time filter h of e to the j omega, which is inside this red box here? Well, we can pick any sampling interval, so let's pick the simplest one, Ts is equal to 1. Xc of j omega, the continuous time spectrum, is equal simply to x of e to the j omega, the 2 pi periodic spectrum, over one period. Yc is simply the product of xc with hc, that's the convolution theorem, and the output y of e to the j omega is equal to yc of j omega. This is summarized in the following equation. Capital Y e to the j omega is equal to the product of x e to the j omega with hc of j omega. So the important point is that hc is the continuous time Fourier transform of the continuous time filter. This is written here, h of e to the j omega is equal to hc of j omega. This is the interesting part, how a continuous time filter maps here into this 2 pi periodic discrete time filter. Let's look at an example with a specific spectrum. Here we have the blue spectrum. It's a discrete time spectrum, so it's 2 pi periodic, but it's only different from 0 between minus 2 pi over 3 and 2 pi over 3. We map it to a continuous time spectrum, xc, which is necessarily between minus omega n and omega n by interpolation, and it is smaller than this particular support because it was not a full spectrum to begin with. We apply a continuous time filter, which is this green spectrum here. The continuous time filter might be not band limited, so that doesn't matter because the input to the filter is band limited, so the result will be band limited as well. And then we have the result in continuous time, which is a modification of the spectrum here, minus omega n and omega n, and it looks slightly different because of the filtering effects that we just applied. Then we sample and we get a discrete time spectrum, the blue one. It lives between minus 2 pi over 3 and 2 pi over 3, and it is a modified spectrum due to the green filtering we had applied earlier. Okay, so here we see all the steps from discrete time spectrum to interpolated continuous time spectrum, filtering of that spectrum, and then sampling again to end up with a 2-pi periodic spectrum modified as given by the filtering operation. Let's look at a concrete example. It's fractional delay. So the fractional delay we know has a discrete time Fourier transform equal to e to the minus j omega d, where d is the delay. If d is an integer, then this is simple. We know how to do this. If d is not an integer, then the impulse response of this filter is the sync sequence delayed by capital D. So to achieve this, you have to reinterpolate the signal and shift by the delay D. So let's look at this. So we have a sequence xn. We interpolate to xc of t. We apply the delay now in continuous time by e to the j capital omega d. This gives us a delayed version yc of t. We sample this and we get yn, the output sequence. In equations, yc is equal to e to the minus j omega d times the continuous time Fourier transform of x, then yc in time domain is simply the delayed version by d. To summarize, yn is a sample interpolation of xn. Let's look at this concretely. We have xn, a sequence indicated in red. We interpolate it with the usual sync interpolation formula. So we have different things given in blue. The result is the red curve, that's xc of t. We delay it to get yc of t. So you see the red curve shifted right a little bit, a fractional delay, so it's less than an integer delay. You resample this delayed version at the same sampling intervals as the input sequence xn to get yn, and we have our delayed sampled version yn. So to delay a discrete time signal by a fraction of a sample, we would need an ideal filter. That would be not so easy to achieve. We're going to see efficient time-variant approximations, but that comes later here in this class. Let us look at one last example, the differentiator, or how to compute the derivative of a signal, in this case, a derivative of a sequence. So that's intriguing because, of course, a sequence doesn't have a derivative, but we know how the derivative would look like in Fourier domain, namely the discrete time filter that would compute the derivative of the equivalent underlying continuous time signal has a discrete time Fourier transform h of e to the j omega equal to j omega between minus pi and pi. So please note that the right side is not 2-pi periodic, but this is only defined on the interval minus pi to pi. So in continuous time, we know the Fourier transform of signal xc, its derivative would be j capital omega capital xc. So we have the same effect on the interval minus pi to pi. That's what we're going to try to achieve in discrete time. So one way is to use duality. We take the sequence xn, we interpolate it with a sync interpolator, we get xc, we multiply in Fourier domain j omega, which corresponds to taking the derivative, so that gives yc, then we sample, we get yn. And truly yn would be the sampled version of the derivative of the interpolated version of the input sequence. Okay, so in equations we have yc is equal to j omega xc. In time domain, yc is equal to x prime c. And as already said, yn is a sampled interpolation of xn, but differentiated. So the discrete time Fourier transform of this differentiator is shown here. So it has this slope of j omega between 0 and pi on this symmetric. The phase response is given here. It has a discontinuity at the origin. We can compute the discrete time differentiator by taking the inverse dTft of the Fourier spectrum we have just seen. So it's the integral between minus pi and pi of j omega e to the j omega and d omega. With a little bit of sweat, namely integration by part, we find that it's a very simple discrete time impulse response. It's 0 at the origin, and then it is equal to -1 to the n over n for n different from 0. A very simple, but of course very slowly decaying impulse response. We see this impulse response here. It's 0 at the origin, and then it alternates and decays as 1 over n on both sides. It's an asymmetric impulse response. To conclude, this digital differentiator is again an ideal filter. We have seen it from its DTFT. It has phase response that is discontinuous, so it will have slowly decaying impulse response, as we have seen after we calculated it. So there are many ways to approximate this, which will have different properties. And one way to do it is to simply use duality and implement differentiation in continuous time. To conclude this module, let's wrap up. So we have seen how to compute discrete time operations in continuous time, or conversely, how to compute continuous time operations in discrete time. In all these cases, we had to jump back and forth between continuous time and discrete time, and we know how to do this using the sampling theorem, namely sampling and interpolation using the sinc kernel. Now, the most common application of what we have seen is indeed to apply discrete time processing on continuous time signals. This happens all the time in real life. It happens right now when I speak with you, because I speak in continuous time. This is processed on a computer, and you listen to it again in continuous time. And we can do all sorts of processing on the computer, which is discrete time processing applied to continuous time signals.